what I wanted to do last time was to provide you with the motivation and then the foundations, right? So the motivation for what we're doing is to provide a foundation for non-relativistic quantum mechanics, or quantum mechanics, but mostly in the non-relativistic context. And that, I think, is a very good motivation. But I left out two other points that came to mind afterwards. So the way that this course was originally designed was by myself as a one semester long course that would culminate in what I thought is the sort of one of the crowning achievements of quantum mechanics, which is to calculate from first principles the decay rate of the excited states of hydrogen. And my understanding is that Mwande has maintained that structure. So there's a certain set of sort of tools and ideas and concepts that you will need in order to be able to do that calculation. And again, it's one of these things that's just unbelievably stunning. You do the leading order calculation and you get the right answer off the bat to 3 figures. It's hopefully when you get there, it will send shivers up your spine. Okay. And another thing that I find really amazing about quantum mechanics, one of the fundamental postulates of quantum mechanics, which we'll cover again in a moment, but hopefully you're familiar with from Tuesday, is this idea of the direct quantization condition, that you're going from the Poisson bracket to the commutator, where the translation has an I. And to my knowledge, this is the only place in the natural world where the square root of -1 comes in a fundamental way, which is kind of amazing, right? Because everything that we see in the natural world is real numbers. So why is a square root of -1, which we never actually measure, why is that involved in some fundamental way in quantum mechanics? Okay, super. All right, so just a brief review. Postulates of quantum mechanics. So we said one, that the state of a system, and I'm just going to be a little bit brief here compared to last time. So the state of the system is represented by psi, which is in a Hilbert space. And we said that a Hilbert space is a complete inner product space. We went through that in some detail the last time. I don't want to necessarily go through that again, but if there are any questions, I'm happy to field them. The completeness is about the idea that you are going to always be able to represent any physical setup in the mathematics of your quantum mechanics. And the inner product tells you about how long vectors are and how much vectors overlap with each other. And this will be very important for reasons that'll be clear in just a moment. So the second postulate is that observables are represented by Hermitian operators whose operator commutation relations are given by some bracket A, B equals C, classical mechanics, goes over to commutator of A and B raised to operator equals I, C raised to an operator. So this is a some bracket, and this is a commutator. And we talked about why we want Hermitian operators, and that's because, as mentioned before, everything that we measure in the real world, we measure real numbers. So we'd like to ensure that the quantities that we measure are not complex. 3. Measurements yield only the eigenvalues of the operators associated with the observable, associated with the observables. And measurements are probabilistic. Which is to say that the probability of measuring some eigenvalue omega, given that one is in a state psi, is proportional to the modulus squared of the overlap of omega with psi. Just a second. And then once a measurement is made, the state collapses. Yes.
Just wanted to clarify notation.
Yeah.
For the plus and minus subscripts of some mutations.
Yes.
Indicating anything in particular?
That's a fair point, because the Poisson bracket also has the relative minus sign. Yeah, it's a bad notation on my part. I'm sorry. Yeah, that's a fair point. Let me get rid of that as a plus. That's, you know what that actually is that's me just not thinking about the anti-commutator, which is also written as a curly brace. So I'm just it's just me being dumb. So thank you. Good. Other questions? All right. Great. And then for time evolution is given by the Schrödinger equation, which is I partial t acting on psi, which can be a function of t, the psi ket. This is the Hamiltonian operator at some time t, and then the ket psi of t again. So I want to reflect for a moment on the idea of these as postulates, as the fundamental underpinnings of the study of quantum mechanics. I think Bjorn and I had a conversation about this yesterday, which I thought was helpful. I hope you also thought was helpful, because I think we sort of forget about the fundamental postulates of, for example, classical mechanics. So you could ask why F equals ma. Why is Newton's second law? Why does Newton's second law describe the natural world? And that's a really, really good question. But that's not a question that you ask within classical mechanics. I'm going to study classical mechanics. My assumption is that motion is given by the equations of motion, which are found from F equals ma. So I want to know where a particle goes as a function of time. I tally up the forces on that particle. That allows me to find the acceleration. I integrate the acceleration with velocity to get the position. That's all of classical mechanics. For us, it's the same thing. You could ask, why is a state of system represented by a state in a Hilbert space? Why are observables represented by Hermitian operators? So on and so forth. And those are good questions. And we'll speak to them a little bit. We spoke a little bit to them on Tuesday. We'll speak to them again some more today. But for the purpose of this class, we're just going to take these as given. They're as fundamental as F equals ma. Okay. Very good. Yes.
In terms of the history of why Dirac quantization multiplied by R,
Yes.
what was the motivation? Was it just like, this makes the maths work? Or is there like, what is the insight that makes us multiply by R? I mean, if this is extremely complex.
So I don't think I have a particularly good answer to your good question. I think an insufficient answer is that we certainly know that classical mechanics works in the regime within which classical mechanics is valid. So when h bar goes to 0, whatever theory we have, if we claim that that theory is valid for all values of h bar, that theory better also be valid when h bar goes to 0. And so we better have a theory that reproduces classical mechanics as h bar goes to 0. And for reasons that you've seen already a little bit in the homework, this Dirac quantization condition is in some sense giving you a natural h bar goes to 0 limit of classical mechanics, that the algebra of quantum mechanics is the same as the algebra of classical mechanics, where you're used to the idea of algebra and quantum mechanics, you're used to the idea of commutators, perhaps less used to the algebra of classical mechanics, which is the algebra of Poisson brackets. But the algebras are identical. Good, thank you. Other questions? All right, great. Find my cursor. All right. So let's continue into new material unless there are last questions so far. And if you questions arise, percolate up, please feel free to ask. All right, let's talk about the expectation value of an operator. So if the system is in a state psi, then the expectation value of an operator, say O hat, when the system is in the state psi. So in general, the expectation value of anything in terms of probability and statistics is over the values you can measure weighted by the probability of measuring that value. And we can, by the nature of what we mean by the inner product of the modulus squared, we know that this is omega psi and then outer product of omega with omega psi, because the inner product with the order swapped is a complex conjugate. And then we can be clever and write this as the operator acting on these eigenstates omega to pull out the eigenvalue. And now we can bring this sum over omega through. And remember, the sum over the eigenstates is just the identity operator. So we can then pull that out. Good. So this is how one can compute. An easy way to compute the expectation value is to sandwich the operator between the bra and ket of the state in which the system is in. And notice how the expectation value is independent of the basis chosen for the Hilbert space. Which better be the case, because the expectation value is something that's physically measurable. The basis is like the coordinate system for our vector space, right? The distance from here to Stellenbosch doesn't depend on whether I lay down coordinates in feet or in meters, whether I use some coordinate system that's natural for the Earth or the coordinate system that's natural for, say, the galaxy. The distance is invariant. Okay. Questions? No questions. Great. Heisenberg uncertainty. Okay, let's define the difference. Say delta sub psi of an operator O hat when the system is in a state psi by this. So I've got my delta sub psi on my operator O. We define this as the operator O minus its expectation value in this particular state. Then the variance of a measurement is given by the expectation value of this difference operator squared again, under the assumption of the expectation value of the state itself. Is my writing getting a little chicken scratchy? Okay, I'll try to be a little bit less sloppy. All right. So if I expand this out, this squared out, so then I get the operator squared minus 2 operator and the expectation value of the operator under psi. And then plus the expectation value of the operator under psi squared. And then expectation value under psi. The notation is a little bit clunky, but I want for clarity rather than concision. That's my general preferred method. Okay. When I take the expectation value of the operator here, I just get the expectation value of the operator squared, and those last two terms will then combine. And so this is then equal to the expectation value of the operator squared minus the expectation value of the operator itself squared. I imagine everybody has seen a formula similar to this before. I'm getting at least one nod, so thank you. Very good. All right. So recall Schwarz's identity. And Schwarz tells us that if I have two vectors in my Hilbert space, say V1 and V2, the length of those two vectors multiplied is always greater than or equal to the length of the overlap between these two squared. So we're going to do some clever footwork here. So thus for two observables, call it A hat and B. These are observables, therefore they are
Permission.
very good permission. Perfect. We're going to have that the expectation value of delta A squared, expectation value of delta B squared. And now I'm being concise with my notation. I'm dropping the size. So if we write this out, this is psi delta A psi, psi delta B psi. And because the operators are Hermitian, I can think about this delta A acting on this psi ket, and this delta A acting on this psi bra, and similarly for the B's. And this delta A acting on psi, that's one vector in the Hilbert space. And then this is its conjugate, and similarly for the delta B on the psi. And so by Schwarz's inequality, I'm guaranteed that this is bigger than or equal to the overlap of psi delta A delta B psi. Is that clear? Give it just a second. All right, great. Now we're going to continue with our fancy footwork. So that was a clever little trick. Let's do a couple more clever tricks. Now, delta A, delta B, in general, that's going to be 1/2 the commutator of delta A with delta B plus 1/2 of the anti-commutator. Here I do mean minus and plus in the right way. Yeah. And if you just work it out, right, so this is delta A, delta B minus delta A, delta B, and this will be delta A, delta B plus delta A, delta B, delta A. And so the ones that are reversed cancel, the ones that are the order we want add, and that's where the halves come in. And further, we have that the commutator of, say, one operator with another operator, Hermitian conjugate, in general is equal to minus itself if the operators are Hermitian. And then the anti-commutator of an operator, one operator with another operator, the Hermitian conjugate, is equal to plus itself. Okay. So what does that mean for us? So therefore, if I look at psi and then say operator 1, operator 2, commutator psi, complex conjugate, that's going to be equal to minus the expectation value of this commutator. And if I look at the anti-commutator and the complex conjugate, I'm going to get a plus. And what does that tell me? It tells me that this first quantity, the expectation value of the commutator, is pure imaginary. And the second quantity is pure real. Right? If the complex conjugate is equal to itself, the quantity is real. If the complex conjugate of the quantity is minus itself, it's pure imaginary. How does that help us? That means that when we look back at this mod squared of the expectation value of delta A, delta B, so we therefore have that this delta A squared, delta B squared, this thing is bigger than or equal to this quantity here. And this thing we can break up into a real part and an imaginary part modulus squared. So we'll get a 1/4 psi commutator delta A, commutator delta A, delta B, modulus squared, plus 1/4 modulus of psi anti-commutator delta A, delta B squared. In the second part, I don't even need a modulus as a real number, but just for notational consistency. Now, the modulus squared of anything is going to be a non-negative number. And so this is necessarily bigger than or equal to just the part that's coming from the commutator. Now, in general, if I look at the commutator of some delta A, delta B, this is the commutator of our operator, and then the expectation value of the operator under our state psi, and then the B operator plus the expectation value of B under the state psi. These expectation values are just C numbers. In fact, they're real numbers. And so commutators of them are just 0. Involving them are just 0. So this is just equal to the commutator of A and B. So let's consider the example of the A operator is the X operator, and the B operator is the momentum operator. Then the commutator of delta X with delta P, this is I, Dirac quantization condition, fundamental postulate of quantum mechanics. And therefore, the expectation value of the variance of X multiplied by the variance of P is greater than or equal to a quarter. If you want, we can, in one of the rare occasions, we can restore our H bars. Be happy. I felt great about this when I was. You've seen this all before? Okay, good.
See.
Okay. Okay. Well, I feel like this is sort of like the sky's open and the light shines down. It feels like an amazing result to me. I hope that at some point this feels like an amazing result to you as well. But if not, that's okay. Are there any questions on what we did? All right. Super. Let's move on to the functions of operators. All right. So we have that an operator maps the vectors of a Hilbert space to themselves, right? So we have that some operator is a map from the vector space to itself. And so in general, we have some dictionary that tells us that for all, say, some vector v in the Hilbert space, the operator acting on v is equal to some other v prime, where v prime is also an element of this vector space. Right? Now, since this v prime is also an element of the vector space, we have a well-defined way to compute the operator squared, which is also an operator going from the vector space to itself, right? That if I want to know what is operator squared on V, well, this is just the operator and then the operator on V. I know how to compute the operator on V. So this is the operator, and then this is my V prime that I talked about before, which is some other vector in the Hilbert space. And I know how the operator acts on some generic vector in the Hilbert space. It gives me some other vector in the Hilbert space, some V double prime, where V double prime is again an element of our vector space. And so I imagine that you can see pretty clearly that we can generalize to any polynomial power of the operator, that that's a well-defined object that itself is an operator, and I know how to compute it. And I get a nod that that's clear. Okay, great. Find way to define the power operator taken to any polynomial power. I guess I took one look and decided it wasn't for them. All right, cool. So that's neat. So now what we can do is we may now define any general function of an operator. Say f of the operator through the Taylor expansion. Of the function f, which is to say that f of some operator, we're going to define this sum n equals 0 to infinity, nth derivative of f evaluated at 0 over n factorial operator O to the power n. I think we covered that yesterday, but are there any questions there? Okay, great. So suppose that we consider the function of an operator, say a hat, in a basis for which a hat is diagonal. So we have our f of a hat is our Taylor expansion. And then we have our a hat to the n. We can always multiply by the one operator on the left and the right. So let's consider some basis. So here's one identity and here's another identity. But our operator is diagonal. So this will be simply a sub m Kronecker delta s m. So we will get this sum and then sum over m of a sub m outer product of am. And it's am to the nth power, excuse me.
Sorry, the second summation, is it contained within the n summation?
Absolutely. But here's where we can do something clever, which is now we can reverse the order of these summations. And so this will be equal to the sum over m of the outer product of m with itself, sum n equals 0 to infinity, fn 0 over n factorial a sub n m to the nth power, where I'm now grouping my sums in this way. And what is this object in the parentheses, if not because a sub m is just some number, some real number even. This is simply the function f evaluated at a sub m. And so we find that this, our function of our operator is just the sum over the outer product of our basis, and then the function evaluated the eigenvalues of the basis. We work in some uncountably infinite number of basis states basis, then we get an integral rather than a sum. And so I hope that you then see one reason why it's very desirable to work in a diagonal basis. Great. Any questions there? Wonderful. Let's work out the matrix elements of the X operator and the P operator in the X basis. All right, so consider a 1D system. On the interval of -infinity to infinity. Then our X operator, excuse me, is Hermitian with a complete orthonormal basis, CON, where the decomposition of unity is given by the integral from -infinity to infinity dx, the outer product of X with itself, and the inner product of X with Y, where both X and Y are eigenkets of the position operator. This is the Dirac delta function. So just to be clear, the X operator acting on the X eigenket gives me the number X multiplied by X eigenket again. And then the X operator acting on the Y eigenket is the Y eigenvalue multiplied by the Y eigenket. And then presumably connected, question? Complete orthonormal. Yeah. It gets a little lengthy to write. Yeah. Okay. So connecting to things that you've seen before, I don't think that this should be news. If it is, we can talk about it. So if I have a state psi, then we can always multiply by 1 or act with the 1 operator on the state. This is the integral dx, outer product of X with itself on psi. And we see this object often enough, this inner product of the X eigenket with state psi, that we call this psi of X. This is now a concrete function, C number function. We call it the wave function. It's simply the state, the abstract vector state in a particular basis, the X basis. So that was all parenthetical as sort of making sure that my objects were well defined in terms of the X and Y eigenkets, and hopefully connecting back to things that you've seen before in undergraduate quantum mechanics. I'm getting one nod, thank you very much. So then the matrix element of the X hat operator in the X basis. This is defined as the X bra, the X hat operator, and then the Y ket. Now, to progress, operators are nasty. Numbers are nice. Anytime we can get rid of an operator and make it a number, we should. Let's not get rid of these. Let's get rid of nasty operator x hat and replace with pleasant C number eigenvalue y. So this is equal to y overlap of x with y. Because we're in a complete orthonormal basis, we know that overlap that's the Dirac delta function. And because the Dirac delta function in a physicist sense is zero whenever x is not equal to y, this statement is equivalent to the statement that this is x Dirac delta x minus y. So that's our matrix element of x in the position basis. We'd like to work out the matrix element of the p operator in the position basis. But maybe we'll just pause. Super. We need to be a bit clever. Work out the matrix element of p hat in the position basis. And I'm going to do it in a slightly different way than what you worked through yesterday or what you will work through in your homework in terms of finding x hat in the momentum basis to give you just a different flavor of things. Both are equally fine. So consider for some epsilon much less than 1, the x hat operator acting on the identity operator plus I epsilon p operator acting on a position eigenket. Again, we don't like operators. We would like to get rid of operators whenever we can. So simply taking the x operator acting on the identity becomes the x operator plus I epsilon x operator p operator acting on the x eigenket. And I can simply replace the x operator acting on the x eigenket as the number x multiplying the identity operator plus I epsilon x hat p hat acting on the x eigenket. Now this xp is nasty because I have two operators, but if I can commute the x past the p, then I can act the x on the x eigenket and replace the x operator with the x eigenvalue. I can't do that for free because I know that xp has a non-zero commutation relation, but I know what that commutation relation is. So this is equal to x1 plus I epsilon, and then xp is the commutator of x with p minus p hat x hat. We know that the commutator with x with p is I, and then p x hat acting on x will give us p hat x. And so my result ultimately is going to be x minus epsilon acting on the identity, multiplying the identity operator, plus I epsilon p hat x, or I guess I could call it I epsilon x p hat, all acting on the x eigenket. And now we're going to do a little bit of fancy footwork and say that this is equal to x minus epsilon multiplying the identity operator plus I epsilon p operator x eigenket plus quantities of order epsilon squared. Thank you. It's honestly really reassuring when people ask questions like that because that means you're getting it. I get worried when I make it catch it. Good. feel like if I was an exceptional teacher, I would put in those mistakes on purpose. Not that good. All right, great. So everybody happy with this line? Good. You see that there's some extra stuff when I multiply this out, where I get this epsilon squared, but that's going in the epsilon squared piece. So we're okay. All right, great. So what that tells us then is I have the x operator acting on this state, this ket, gives me x minus epsilon, and then the same ket again. What does that mean? It means that this ket is an eigenket with an eigenvalue of x minus epsilon. And what do we denote eigenkets of the x operator with a particular eigenvalue? We just name it what the eigenvalue is. So since x hat on this thing is equal to itself with an eigenvalue of x minus epsilon, we therefore have that this vector in the Hilbert space is eigenket of the x operator with eigenvalue of x minus epsilon. So we call it the eigenket x minus epsilon. Now, a clever trick that we will exploit over and over and over again is exponentiating infinitesimals. Because in general, not in general, but almost always, it's easier to work with infinitesimals. You have to work to leading order in the smallness, and then you just throw everything else away. But you'd like to ultimately have some transformation that is finite. And you do that by having an infinite number of infinitesimal transformations. So somewhat parenthetically, one may build up a finite translation by, say, A, by acting an infinite number of infinitesimal translations. So we could examine the limit, just one second, the limit n goes to infinity of 1 plus I a or n p hat raised to the nth power, and say I have this act on x, and that's going to be e to the I a p hat acting on x, where we know what a function of an operator means by a Taylor expansion, and that this will be equal to minus a. Yeah, there was a question.
Sorry, no, I was just thinking out loud. I was like, just understood what that statement means.
Cool. Questions? All right. It's a little abstract, might be a little unfamiliar. That's actually okay. With practice, the goal will be that you'll become familiar with it, and then you'll be like, oh, I understand this. Because what is understanding is really just familiar, honestly. All right, especially when it comes to quantum mechanics, which is brain melting and totally wild and completely different from our normal everyday classical experience. All right, great. So let's now consider what happens when we have an x bra hitting our identity plus I epsilon momentum operator acting on this, the ket psi. So I can think about this in two different equivalent ways. I can think about bringing the x through, and then I get the overlap of x with psi plus I epsilon x p hat psi. But from what we just discussed, I also know that this left-hand side is x plus epsilon on psi, which is, according to us, the wave function of the state psi evaluated x plus epsilon. And any function of some stuff, I can always Taylor expand. So this is psi of x plus the derivative of psi with respect to x multiplied by epsilon plus epsilon squared. And I can then match these quantities order by order in epsilon. So I get self-consistently that psi of x is equal to the overlap of x with psi. And then I get that I x p hat psi is equal to d psi dx. Everything okay? And it's okay if it's a little... Okay. Can you point to where things started to go off the rails for you? So I'm just going to consider this. Are you happy with the right-hand side?
No,
Okay, so I'm going to get an x1 psi plus x I epsilon p. One is just, I'm sorry?
The one half operator has eigenvalue 1.
okay.
The one really, so it's the one operator. So it's just giving me the vector back. Yeah, you're welcome. Good. That's the most important operator. So we better like be on the same page with it. And I'm glad we're there now. Good. Other questions? Yes.
The equation underneath is psi brackets x plus epsilon.
Yes.
Is it psi the function of x plus epsilon?
Yeah.
Yes. Yeah, exactly. So remember that we talked about how we define the wave function as the overlap of x with psi. And so if I simply replace the variable x with the x plus epsilon, it just runs through. Very good. Great. Yeah, no, please go ahead. Yeah, no, this is great.
Is the one operator yeah, I'm still confused with marketing today. Does it not need to act on side to give back side?
Yeah, absolutely.
Okay. Is that a plus? Should,
So this is there's a plus here. And so I end up with a plus here. You're welcome. Maybe it would help if I put a parenthesis or parentheses here.
Yeah.
Okay, great. You're welcome. Yes.
One thing I'm thinking about is that we wrote down the state x plus epsilon dual vector
Over here.
just on the left of it. But previously we worked out
Oh,
state x minus epsilon. I don't know if I'm missing something.
well, let's check. So I've got that 1 plus I epsilon on x ket gives me an x minus epsilon ket. And so now if I'm going to act on, if I'm going to think about, say, taking the Hermitian conjugate of this whole thing. So if I take the Hermitian conjugate of this whole thing.
Okay.
Yep, good.
Thanks.
It's a sign. Signs are very tricky.
Yes.
Yeah. Good. Other questions? All right, super. Okay, so the punchline is that if I have the x bra p operator and then any general state psi ket is equal to minus I derivative of the psi wave function with respect to x. Okay. Let's do one of the very few things we can always do, which is insert a 1. So x p hat psi, this is x p hat, and then the 1 operator psi, those two acting together. And then I'm free to write my 1 however I want, and I'd like to write it as a 1 in the y, or rather the x basis. And so this will be bringing the integral out. The matrix element of P that I'm interested in, and then I've got my wave function now as a function of psi. And I'd like to connect this result here with the previous one that I have up here. Now,
So you
Yes.
say it's a size of function of y.
yep, good. And all good? Great. Everybody's felt comfortable with through, yes? So I'm just saying that,
Oh, it's a nutritious factor 1. It's the y ket y bra.
yep. Great. I like that nutritious factor of 1.
That's Andre's Pesce's phrase.
All right, very good. So everybody said that I believe everybody said they were comfortable with Dirac delta functions yesterday. Are people comfortable with derivatives of Dirac delta functions? Have you seen that before? Okay, fine. So just as a quick aside, so integral dx delta x minus a f of x, that's f of a. And let's be a little bit careful. So on and so like so. So if I have the integral minus infinity to dx of d by dx delta x minus a f of x, I don't necessarily know how to deal with that as it's written, but I can always integrate by parts. So this is going to be equal to d by, well, it's equal to delta of x minus a f of x evaluated at x is minus infinity to plus infinity minus the integral minus infinity to infinity dx delta x minus a. Run out of space. D by dx f of x. IBP, integration by parts. I had a friend in grad school who realized, he did a quick calculation in his head. He says, I've integrated by parts on average once a day for my entire life. Moving on. Okay, so we're assuming our test function falls off fast enough at infinity. Also, the delta is itself 0 at infinity. So this is just 0. And then this derivative of f is itself just some function of x, assuming that f is sufficiently smooth. We're physicists. We're not going to worry too much about things like that. And so then we're able to collapse the Dirac delta function. And this then becomes minus f prime of a. What we can do, coming back to what we had before, we derived that this overlap of x p hat psi is minus I d psi dx. And we have here some integral dy, some object, and then the psi of y. And so can you see that this x p hat y, if this is up to factors of minus signs, the derivative of a Dirac delta function, that will give us the correct answer. That will reproduce the known results. So getting the right sign, this is going to be equal to I Dirac delta prime of y minus x, which is I d by d y delta y minus x, which we can also equivalently write as minus I d by d x. Let's see. Good. D by dx delta x minus y, which is I d by dx. No, I'm being silly. All right, let's not look at my notes because my notes are making minus mistakes. All right, so I've got I derivative of the Dirac delta function y minus x. So it's I d by dy of delta y minus x. So it's minus I d by dx delta y minus x, which is plus d by dx delta x minus y, which is equal to minus I d by dy delta x minus y. These are all equivalent. Maybe something that's of potential value for you as you some qualitative insight into the delta function. So if I have x and I have delta of x, then this is an even function. And so that tells me then, if I look at the derivative of the delta function, that this is going to be, okay, so this is the slope of it. So it's a positive slope going to infinite positive, and then it's a negative infinity going down to just barely zero. So it's an odd function that looks like this. And so that's what's happening here. I can always, if it's just a delta function, I can swap the arguments and not change anything. But if I have a delta prime, if I swap the order of the arguments, I pick up a minus sign. Good. So this should be kind of amazing, right? To have derived this matrix element. And I hope that it's not too like, oh my God, derivatives of Dirac delta function. That hopefully it's kind of like, oh my God, that's really cool.
So,
Yes.
so based on the odd and even explanation you gave us, second last equal sign actually minus I.
Let me see. So I have let me just go through it step by step. So I've got the I derivative of the Dirac delta y minus x. So this is I d by dy of Dirac y minus x. And if I swap the derivative with respect to y with the derivative with respect to x, then I pick up a minus sign, chain rule. Okay, great. Good. Welcome. Yes.
The quality that for x, you operate at y with I.
And so I just want to clarify. So is this like a mathy question of like, how am I rigorously defining this as an equality?
No, it's
Okay, well, let's start with this expression here and plug in what we have for the have and see if we get the right answer. All right. So let's start with this. And the claim is that this is equal to, now I'll just get rid of this, and I put in this object. And if all is right in the world and all my signs were done correctly, then we're going to get back the known right answer, which is this. So we better get at the bottom of our calculation that.
Yeah.
Okay, good. So this is equal to the integral dy I d by dy delta y minus x psi of y. Now I don't know what to do with the derivative of a Dirac delta function. I only know what to do with the Dirac delta function, so I integrate by parts. So then dropping boundary, because the delta at infinity is 0. This is minus I integral dy delta y minus x d psi dy. And great, that's exactly what I promised it would be when I collapse the delta function. Other questions? Okay, so maybe as another example of, I'm getting a little bit ahead of myself in terms of the postulates. I'm trying to go through the postulates order by order. The last is the time-dependent Schrödinger equation. But this form that you've usually seen it in is probably the time-dependent Schrödinger wave equation. You have the minus grad squared over 2m plus v of x psi of x. And the question is, where does that come from? So I'd like to show where that comes from, coming from the time-dependent Schrödinger equation as an application of using these Dirac deltas or the matrix elements of the momentum operating position basis. Yeah.
So that only is to then good data. It's good. Do you think it's really easy to generalize this to
Well, as soon as you asked a question, my heart rate went up. And so easy is perhaps not, it's certainly not trivial. But I think we could be able to figure it out pretty quickly. And in particular, it should end up being, rather than sort of in some sense a trivial derivative of Dirac delta, it'll end up being a gradient of the Dirac delta. I think that should be relatively clear. So if I thought about this higher dimensions. So I suspect it's pretty clear that if we add a vector there, then what's going to happen over on the right-hand side, the different dimensions are not going to talk to each other. Get a vector on the right-hand side, a vector of derivatives with respect to the different directions. So this is going to then become minus I gradient with respect to x acting on psi of x. Okay, cool. And so then our x p vector hat y, this is going to be equal to I gradient with respect to, let me get my signs right. Yeah, I gradient with respect to x. Now, n-dimensional Dirac delta function x minus y. Great. Other question? Thank you. Okay. So brief aside on the time-dependent Schrödinger wave equation. So postulate 4 said I partial t on psi of t is equal to the Hamiltonian operator at time t acting on the state psi of t. And suppose that the Hamiltonian operator is p hat squared over 2m plus potential, which is only a function of the position operator. Then I partial t psi t is equal to p hat squared over 2m plus Vx, all acting on psi of t. And I can always hit this on the left with an x bra. So I have an x bra, I partial t, psi t equals x bra, p hat squared over 2m plus v of x, psi of t. I can pull out the I partial t, and then I have I partial t of the function at time t in the x basis. So this is going to be equal to x, and then the same stuff as before. We insert our nutritious identity. And what's going to happen with that nutritious identity? For the v as a function of the position operator acting on the y, well, we're in a basis where the operator is diagonal. And so I can simply replace the v as a function of the operator with the v of the eigenvalue. Then for the p hat squared, that's going to be a little bit trickier. So this is our integral dy, 1 over 2m x p hat, and if you want, you could do p hat y plus, so x vxy, and all of this is hitting my psi of y and t. And we said that this is just going to be equal to, so our x v hat y, this is vy delta x minus y. And our x p hat y, this is going to be equal to minus derivative with respect to y squared delta x minus y. If you want, I could insert, I'm doing implicitly two things. I'm inserting an additional one in between here, getting a Dirac delta prime, and then I'm going to get another derivative from the other p hat. I'm just doing that twice. Two i's give me a -1. You're looking kind of, okay. Good. So bringing this down. It's going to be equal to then integrate by parts twice, collapse the delta function, -1 over 2m dx squared plus vx acting on psi of x t. I did take some of those bits quickly. I could go more slowly if you would like. Yes.
Please just give a verbal explanation again. So we integrate by parts and then.
So I'm replacing my matrix element of p squared operator by minus derivative with respect to y squared Dirac delta function. I don't know how to deal with this object, so I integrate by parts once, yielding a partial y delta x minus y. Still don't know what to do, so I integrate by parts again, and I'll get then a delta x minus y. I get one minus sign for the first integration by parts, and a second minus sign from the second integration by parts. So I end up with a -1 over 2m, two derivatives with respect to x. You're welcome. Good. Great. Let's continue down this journey where maybe to give some contextualization, some further contextualization, there are certain results that maybe were derived from for you in the past, but certainly you just sort of know from undergraduate quantum mechanics. And I want to show where those results, those canonical quantum mechanics results, come from purely from the postulates of quantum mechanics, no other assumptions. So now let's consider or ask, what is the momentum eigenket in the position basis? So i.e., what is the inner product of x with p, right? This is the wave function for the momentum eigenket. And as we'll discuss further later, it's precisely this inner product that's going to help us or tell us how we could perform a similarity transform or a change of basis from one basis, which is the position basis, to another basis, the momentum basis, for functions. So functions are abstract vectors in an abstract vector space. We can ask, what are those functions in a particular basis, like the position basis? We could ask, what are those functions in the momentum basis? And we can ask, how can we transition between those two? And from your sort of just understanding, general understanding of math, what do you think that transformation is? It's the Fourier transform, yeah. So in this language, the Fourier transform is just one of many different change of bases that one can have in describing functions which live in a vector space. Cool. Good. So more fancy footwork. So consider x bra momentum operator, momentum eigenket in two ways. As always, we want to get rid of the operatorness. That's always hard. So what's the easy way to get rid of the operatorness of this P in this particular expression?
Spell out the momentum eigenstate.
Spell out the momentum eigenvalue.
Eigenvalue.
Yeah, exactly, exactly. Very good. So this is P overlap X with P. Okay, great. Now, we previously labored to show that for any general state psi ket, x p hat psi ket is minus I d psi d x. So we can use that also. This is also equal to, and I've already lost the sign, but presumably my sign is right in my notes, minus I d by dx of xp. I can maybe write this in a more familiar way in terms of, or maybe think about this in terms of differential equations, right? So this might look a little bit weird where I've got this symbol overlap with x and p, but if I just call this f of x, you'd be very happy, right? Because I would have minus I d by dx f of x equals p f of x. And can you solve for that f of x? Yes, the answer is exactly. So therefore, we must have that xp is equal to some number e to the I p x. Where this n is some normalization. And I mean this in a way that's supposed to make this feel more comfortable and not to make you feel bad. So by air quotes, trivial ODEs. Right, so I want this to make the connection to something that is very familiar, deeply familiar to you, that you've been doing for many, many years. It's just written in kind of a scary way with this overlap of x and p. But x and p is just some function of x. All right, great. So now we need to figure out what this n is. So to determine n, we require that the overlap of x with y, this is equal to Dirac delta x minus y. We can always insert our ones. So this is x integral dp, outer product of p with itself, y. So this is the integral dp of xp py. So this is the mod squared n integral minus infinity to infinity. I'm just restoring the infinities. And then e to the I p x minus y, right? We have that xp is n e to the I p x from above. And then py is going to be the complex conjugate of n e to the I p y. So we get n star e to the minus I p y. So we get mod squared n and then e to the I p x minus y. Have you folks ever explicitly worked out this integral and shown that it's related to a Dirac delta function? Okay, we'll give that to you in homework. The trick is to add a small convergence factor. That convergence factor goes to 0, and then show that if x is not equal to y, then it's 0. If x equals y, it's equal to infinity. And then the integral over, say, x minus y gives you 1.
When you say convergence factor, on this technique.
Feynman had a lot of techniques.
So
So what are you thinking about?
Technique to differentiate.
No. All right. Anyway, so trust me, for now, you'll be able to engage with this in some detail in the homework. That this is n squared 2 pi delta x minus y. Yeah.
Yeah, I was going to say use
Yeah, these are all sort of, like equivalent definitions of various things. Yeah. So yes, you may know that the EVI PXs are linearly independent for different P's. And what does that mean? It means that the overlap of one with another is 0 if the harmonics are different, or if they are the same, then it's actually infinity. But the question is, how big is that infinity? And it's 2 pi. Okay, cool. Good. So coming back to what we said, so we're requiring that x, or we know that because x and y are a complete orthonormal basis, complete orthonormality in our context means that the overlap of x with y is a Dirac delta function with a coefficient of 1. And we have found that with our momentum eigenstates in the position basis, that we get mod n squared 2 pi Dirac delta x minus y. So therefore, we have to take, that the mod of n squared is equal to 1 over 2 pi. So that tells us then that n is equal to 1 over the square root of 2 pi and some phase factor. But we can take that phase factor to be 1. And we'll talk more about phase factors later. So therefore, I guess let me just be a little bit more careful. So choose to take phi equals 0. So x p is 1 over root 2 pi e to the I px. All right. Super. Any questions on that? Um. All right, we're going to shift gears a little bit and talk about some mathematical subtleties, which might be entirely boring to you or might be super duper interesting. I hope that even for the people who are not super mathematically inclined, that this will still be of interest. All right. All good?
This shit's crazy.
Yeah. Reach. Yeah. When are we going to get to the part that's really mind melting? We'll get to the mind melty stuff on Monday. Yeah. Yeah. Not Monday, Tuesday. All right. So observables and Hermitian operators. All right. So I tried to motivate the postulates. So we're taking the postulates as postulates, but I wanted to give some good reasons why those postulates are the way that they are. And that in some sense, or I guess the question is, to what extent can we still do quantum mechanics and change those assumptions? So one question is, must our observables be represented by Hermitian operators? And before we get to that question, let's start with a mathematical subtlety. The subtlety is often not discussed because it's has to do with infinite dimensional vector spaces, sort of fairly deep ideas in functional analysis. And at the end of the day, it actually doesn't make a very big difference. But I wanted to introduce you to the topic so the words are in your brain. So that if somebody talks about these things, you'll have heard of these things. Or if you come across a certain subtlety and you can't figure it out, that maybe this might be a clue as to why things are going pear-shaped. Okay. So it's a subtlety related to infinite dimensional vector spaces. All right. So if we're being mathematically careful, when we define an operator, on our Hilbert space, well, on a vector space, let's go with Hilbert space. Hilbert space, we need to define not only how the operator acts on the vectors in the space, but also for which vectors in the space the operator is defined. Which we call the domain of definition. Say D of O, which is a dense subset of our H. So if we call this a Hilbert space H. In finite dimensional vector spaces, your operators are going to be defined, well-defined for all the vectors in space. But when we go to infinite dimensional vector spaces, there are these subtleties, especially associated with the behavior of functions out at infinity. They fall off fast enough. And so you can imagine defining operators that mess up the way these functions fall off at infinity. And so you could imagine an operator that takes you away from that nice behavior at infinity. And so there be some functions for which the operator acting on that function gives you a function that's no longer in your vector space. And so that original function is not in the domain of definition of the operator itself. Okay, so now you're seeing how it's very subtle. Okay, and now it's even more subtle is so in infinite dimensional Hilbert spaces, the operator O hat dagger defined by the Hermitian conjugate of the operator O hat may have a different domain of definition. Say D O hat dagger not equal to the domain of definition of O. And the domain of definition of the original operator. And generally speaking, the domain of definition of the Hermitian conjugate is in fact bigger than the domain of definition of the operator itself. It's pretty weird. Now, if our operator is equal to its Hermitian conjugate, i.e., if on their mutual domains of definition, the operator on a vector gets the same thing as the Hermitian conjugate of the operator on the dual of that vector. In the usual way, we call the operator Hermitian. If, in addition, the domain of definition of the Hermitian conjugate operator is the same as the domain of definition of the operator, we call the operator is self-adjoint. Now, in finite dimensional vector spaces, Hermitian and self-adjoint are the same, but there can be differences in infinite dimensional vector spaces. Yes.
Is it true that the domains can only be equal if the operator is Hermitian?
So the point is that self-adjointness is a stronger restriction on the types of operators than just Hermitian. So any self-adjoint operator is Hermitian, not all Hermitian operators are self-adjoint. Good, great. Certain operators we really care about. Other way. So all self-adjoint operators are Hermitian, but not all Hermitian operators are self-adjoint. So you can have certain operators that we really care about. We would just 1 second. So certain operators we really care about, such as the momentum operator, are Hermitian, but not self-adjoining. right? So what does that mean? It means that the momentum operator acting on a state gives you some other state. So the momentum on a state in its domain of definition gives you some other state living in the open space. Now, if I ask what happens to this momentum operator acting on that same vector in the dual space, I get some other vector, which is the dual of the vector that the p hat on the original vector gives you. Complicated, but I think you know what I mean, right? But the point is that the set of vectors in the dual space that the momentum operator sensibly acts on is bigger than the set of operators that a set of vectors that the momentum operator acts on in the space itself. So it's subtle, it's not easy. I don't want to get into the super nitty-gritty details. I'll come back to you in just a second. But I'm going to give you some resources if you really want to read up on the nitty-gritty details of this, which generally has to do with basically integration by parts and what happens in functions. Does that clarify for you? Correct. No. Right, so that is the canonical example. So the momentum operator is Hermitian, but it's not a joint because the domain of definition of P dagger is bigger than the domain of definition of P. So let me just suggest, I'll give a couple references, take a look at those. And if it's still confusing, then let's talk about it after. I think specific examples will help clarify. Okay, great. Good. So this subtle difference between Hermitian and self-adjoint and self-adjoint has something intriguing. But not very worrisome consequences. Which is to say that we can basically ignore worrying about these consequences. That's why nobody tells you about this stuff in undergraduate quantum mechanics, for example. All right. So for example, the eigenvectors of Hermitian, but not self-adjoint operators. Don't live in the vector space itself. Yeah, exactly. Rather, they live in a larger vector space. Which makes up what's known as a rigged Hilbert space. Which forms one part of what's known as a Gelfand triple. So there's no reason why you would know what a rigged Hilbert space is. There's no reason why you would know what a Gelfand triple is. Again, I just want to transmit those words into your brain so that you've heard them at least once. You can Google them, for example. And this is actually something that you're aware of. We literally were talking about it just a moment ago. So what are the wave functions for the eigenstates of the momentum operator, the e to the I the x's? But those are not normalizable in L2 sense. But we can still use them as basis for our Hilbert space itself. Right, so the subtlety is innocuous. Because even though the eigenvectors live outside the Hilbert space, they may still be used as basis vectors. For the space. Yeah,
So, let's.
yeah,
Basis states on the line. So, yeah.
right.
And you not the only one.
So can you construct nicely normalizable momentum wave functions? You can construct normalized wave packets, which I probably have done at some point in your life, where that's an integral over these e to the I px's, but there's no single p for which that's an eigenstate of the momentum operator.
Then I guess the way it happens.
Yes, exactly. Yes, good.
So just to clarify, it's kind of like an expansion of what a basis needs to be. Like it just needs to have linearly independent. Every vector in the space is a linear combination of the basis vectors, but the basis vectors do not have to be elements of the space.
Exactly. It's wild, isn't it?
That is.
Yeah.
Is there really nowhere where we say that the elements of the basis have to be in the space? I swear, like I've seen that before.
It's certainly the usual way of operating. But if you want to do quantum mechanics and you want to do quantum mechanics so if you want to do quantum mechanics in highly restricted spaces, so like the infinite potential well, then you end up not having to worry about these kinds of subtleties. But if you want to approximate quantum mechanics on some large space that is best thought about as one minus infinity to infinity, these are the mathematical subtleties that can and do crop up, but mercifully are, just rather obvious. Yeah, so the way that I wrote it down in my notes is like, I'm going to lift the rug for you, and we're very quickly just put it back down. All right, good. Let me note for you some potential resources. So for more information, see quant tash ph quant phys 9907069, which is titled Mathematical Surprises and Dirac's Formalism in Quantum Mechanics. And quant pH 0103153, self-adjoint extensions of operators and the teaching of quantum mechanics. Okay. Yes,
Silly question.
no such thing,
So. Yeah,
except for first years. except for first year engineers. Sorry, please go ahead. Yeah.
What's
That's exactly sort of the flipping of the rug back down. That there are certain quirky things that can happen that you're generally not going to run into. And so that's why I'm having this as kind of an aside where I introduce you to these concepts, but I'm not going to belabor them in any way. Because just like as you've done in Griffiths, you can work with these eigenvectors as if they live in the vector space, and you really don't have to work that way.
what situation?
Take a look at the references. Yeah. Good. Great. I want to sneak one last concept in before which will finish out the section on subtleties and do operators need to be Hermitian. So if you want to be strictly super mathematically careful and very make sure that everything is going to absolutely work without any subtleties, such that, for example, your eigenvectors live in the vector space itself, then you need to ensure that your operators are not actually Hermitian. They need to actually be more restrictive. It's really have to be self-adjoint. But can we go the other direction? Can we ask, what are the like really important properties that we require of our operators? And can we do something less restrictive even than hermiticity? And the point is, we really care about real eigenvalues and completeness of eigenvectors. So actually relax our restriction on our operator observables away from hermiticity. Really care about the reality of eigenvalues and the completeness eigenkets. And it turns out that in many cases, one only needs the Hamiltonian to be parity and time inversion symmetric PT to ensure the reality of eigenvalues and the completeness of eigenkets. And people claim, and I think it's probably true, that this with PT quantum mechanics, this has been one of the most interesting and active areas of research in quantum mechanics in recent years. So PT quantum mechanics, the first example of PT quantum mechanics was published in '98. And if you'd like to see a review article, PT quantum mechanics, see archive 2312, 17386. title, PT symmetric quantum mechanics. Huh, that's odd. Maybe I'm out of charge. That's a first. Okay. PT symmetric quantum mechanics. By one of the founders of the field. And to give you a sense of the level, so this article is what? 14 months old, and it has over 1,000 citations. Yeah. So it's a very active area of research. Okay, that's a good stopping point. Any last questions before we wrap it up? Awesome. All right.